well, remotely, not here, but Armagan is with us. I'm really happy to have Armagan speaking about microservices because I know he has a very long experience, actually in-depth experience with microservices. He also does a lot of cool things, one of them including software craft school for women engineers, which is really cool. And he's coming from Berlin, so that will be interesting. Thank you, Armagan, for coming, and
thank you.
Let's get started.
Perfect. Now, obviously, this is awkward for everybody. This is also my first time doing a remote conference, online conference. So please bear with me if we do any mistakes or if there are any glitches. So this is Arman. Thank you, Alex, for the introduction. I come from Berlin. I'm currently in Berlin in quarantine. And today I'm going to be talking about the 5 rules of microservices. Now, the topic is really huge, microservices, and apparently everybody understands different things from it. And I want to clarify the most essential features of microservice architecture, and not only in terms of software design, but also in terms of how you maintain that system and how you deploy it and how you manage those services. But before we jump into the topic, a little bit about myself. I'm, again, Arman, a software architect from Berlin. And in my career, I've led several companies as a CTO, as engineering managers, and obviously as developers and architects. I also do mentorship a lot. And currently, I'm most involved with something called Lonja Works, which is a software craftsmanship school for women. And we've been operating for about 5 years now. We have a lot of graduates. And we also do software development for companies as well. I'm active on GitHub. I love open source. Pretty much everything I do nowadays is open source, is available on GitHub. And if you want to follow or be a part of them, I'm mainly into JavaScript technologies, but I have frameworks from brain signal processing to audio applications, to guitar pedals, to front-end applications, and obviously for microservices. Actually, Code is one of the first microservices library for Node.js that I wrote back in 2013. So it's been some time I'm involved in microservices. All right, so what are we going to talk about today? Today, we're going to be mostly talking about what is and is not a microservice. And to demonstrate what I'm talking about, I'm going to be giving you an example of an e-commerce application, a very small one, obviously, that doesn't really have a lot of stuff going on in it, so it's easy to visualize and easy to understand. And on top of that example, I'm going to be talking about the 5 rules of microservices. Now, obviously, there will be a lot more than 5, but we're going to be covering the most essential ones today. And then we're going to be talking about the contemporary tools that people use out in the ecosystem, and to also manage and maintain microservices. And we're going to be seeing how the best practices of microservices are implemented in this case. All right, so let's start with the definition of what not a microservice is. What is not a microservice? Your application that relies on queues and other asynchronous systems is not microservices. Your application that has different queue consumers, like 50 queue consumers for notifications, logging, reconciliation, other services, shipment, tracking, emailing, etc., doesn't actually mean that you have microservices. They're just queue consumers, and there is a reason for the split, and I'm going to be talking about that in a little bit. Also, multiple programs running on a single machine and communicating over HTTP in some form or another is also not entirely microservices. It might feel like I didn't really leave much context here for or any space for what microservices are. That's why now we're going to be talking about what is a microservice, what a microservice is. So the baseline of any microservices application is how you process the incoming requests from a user. So a user is browsing your web application, and they're sending requests to your web server, right? For example, somebody's clicking the buy button, and then there are a lot of processes that are triggered in the backend that the user is going through actually, but they don't know all of those. So you check if their credit card is valid, if it has enough balance on it, and if you have that item in the inventory, or if you can actually ship it, what the shipment dates are. Maybe you want to calculate tax or shipment prices based on the location of the user and the address of the user. So there are all of these steps that you have to do when somebody clicks that buy button. And usually what happens is this whole series of process happens in one single process, in application process. And that is what we call a monolith. Now, what a microservice is, or what happens when you break this single request down into multiple services that run in their own memory space, and they collaborate on finding the response to that user, that is when you get microservices. So again, if these services collaborate with one each other, the shipment service, the inventory service, and whatever service you have, the tax service, if all of these collaborate with each other and form the response or decide what the response should be when you send it to the customer, then you achieve a microservices architecture. Anything else you do is just distributed applications. Unfortunately, the term microservices is bloated. Anytime anybody does a distributed application nowadays, they call it microservices. But unfortunately, the true definition of the term relies on a single request being broken down into pieces and different services fulfilling the different aspects of that same request. Now, this is what actual microservices are, and we're going to be basing our discussion on this. Before we jump into the most awaited rules of microservices, I want to talk about a little bit about the best practices of microservices architecture. Now, this has been mentioned today as well previously. The quality of your approach, of your microservices architecture, actually depends on how well you apply domain-driven design practices to your software. Now, in the previous talk, Alex also talked about encapsulation, modular architecture. All of those combined with domain-driven design make a good microservices architecture. Now, domain-driven design obviously is around maybe for 20 years, and it's not new, but actually being able to use a well-known architecture in a microservices, in like next generation architecture, actually shows you how timeless the original design was, how timeless domain-driven design was. And I'm not going to go into the details of what domain-driven design is. Obviously, most of you already know. And for those who don't know, there's a book called Domain-Driven Design, which is perfect. I encourage you to read it many times, over and over again, because on every read, you actually learn something else from that book. And what I'm going to talk about a little bit is the other cultural changes that you need to embrace when you embrace microservices. Now, a lot of people sell the idea of microservices as a technical choice. And unfortunately, I can tell you it's not the best technical choice. Like if we were after technical architectural choices, one might argue that there are better alternatives than microservices. But why we choose microservices in this age, in 2020, is because of cultural reasons. Now, I have another talk just based on this, the cultural adoption of microservices and what you need to do in order to adopt microservices truly in your application or in your company, let's say. because Conway's law is present in everything we do. Conway's law, which states that an organization will design systems that copy the organizational structure of that company, of that organization. So your microservices are what your company is. So in order to be successful with microservices, the first thing you have to do is embrace change. Everything will change and you won't be able to control it anymore. Different teams will be developing different microservices, and all of these teams will be deploying to production whenever they want. You won't be able to coordinate deployments to production. Now, this feels like it's going to bring a lot of technical challenges. It does, but it also brings a lot of cultural challenges. Are you informing the teams that need to be informed about your application, about your deployment? Are you tracking your dependencies? Now, these things are a lot harder than they sound. To solve these things is a lot harder, because you have to give autonomy to teams and to individual services. They have to be independent of each other. They have to operate individually, independently. Teams have to decide on their own what to do, what to ship, when to ship, which features to prioritize, and what dependencies they have, and what dependencies they are breaking, what dependencies they're using. Maybe you have an array of huge libraries for monolith application. Maybe when you go to microservices, the users, the service implementers won't be using them. So you have to understand that people will be autonomous. And obviously, you will have to automate everything. You cannot manage things that you don't know. You can only automate them. So you have to automate testing, you have to automate configuration, deployment, monitoring, and reactions to monitoring. So emergency room is replaced by automated systems, or your network operations center is replaced by automated systems. And finally, obviously, you have to favor kettle over pet. Now, I'm not going to be talking much about this, but it basically suggests that you shouldn't be treating your servers as pets, like by name, that server over there, or that number, that database server over there, but you should be treating them as cattle, which means that they might be replaceable. Like, you don't really know them by name. You just know how many you have, and then you just breed new ones when you need new ones, and then you sell off some when you need some money. So these things are the baselines of cultural adoption for microservices. Now, let's get to the meat of it. I'm going to be talking about an example e-commerce application. And in this application, you can see that we have at the center an API gateway, which is like a load balancer, which decides which requests will be routed to where. And we have an admin interface, and we have an end user interface. The end users, the customers, are using the end user interface, and the admins, the operators of the system, are using the admin interface. But in the end, they're talking to the same services behind the gateway. Now, let's assume we have a couple of services here. Obviously, there are many more, but these are just the examples that I'm using today. We have a purchase service that deals with the new purchases or past purchases of your customers. We have a user service that fetches the details of a user, or their address, updates the address, and so on and so forth. We have a product service that maybe keep tracks of the inventory or the catalog. Obviously, again, these are not even bounded contexts. Like, these are very, very broad areas of responsibilities. These are not entirely microservices, but assume that these are tiny microservices in the array of hundreds of them in this application. And maybe you have a payment service. Now, a user or an admin doesn't really automatically talk to the payment service. But what they do is they fetch purchases. Or for an end user, for a customer does make a new purchase. So when they make a new purchase, the purchase system talks to the user service, fetches credit card details and other details like the address and others. And then, for example, talks to the payment service and says, hey, I want to charge this user this many dollars. Is it possible? And can you do it for me? And then the payment service talks to database, talks to obviously other payment providers and other services, and then returns a response to the purchase service. Now, for this one purchase request, the end user is utilizing two things. The purchase service, well, three things. Purchase service, the user service, and payment service. But those two are in the scenario behind the purchase service. Obviously, you might be updating your details, your address and everything, your credit card details, for example, that could go through the user service directly. So that's why there is a direct link between the API gateway and the user service. Okay, now, the first rule we're going to talk about is auto-discovery. Your microservices application has to have something called auto-discovery. And basically, this allows you to introduce new services into the system without redeploying the previous ones. Because remember, in monoliths, what you do is you deploy your applications one at a time. And when you want to deploy a new service, like in this case, the log service that appeared on the screen, what we do is we redeploy the entire application. Now, the product service has nothing to do with the log service so far. And it didn't really need to be deployed, if you will. Why are we redeploying everything all together? Now, in microservices, you should be able to automate your deployments. Individual services should be able to deploy individually. And what is more important is other services without reconfiguration should be able to discover the new service. In this case, I'm not very imaginative. I just introduced the log service. And in this case, what I do is the log service is supposed to collect data from other services. And in this picture, you see now introduced log service. Everything stayed the same, but they started talking to the log service. Maybe they were publishing their to a centralized service and we have a new one. Or maybe they were sending events to a system and we have a new one. Or maybe, this is the better option, maybe we preemptively deployed those services and we had a feature toggle that we can turn on and off that they start streaming data to the log service. Or even better, the log service sends them a message and says, hey, I'm online, I'm ready to pick up logs. So, whatever happens in your application, please send them to me. And this is how the other services start to talk to the log service. This is the first rule of microservices, auto-discovery. So you should be able to introduce a new system, a new service into your system, and all the other services in your application should be able to talk to it and communicate with it without a change of configuration, which is basically the next rule. The second rule is zero configuration. Now, whenever you want to make a change in your system, as in deploying a new service, all of these things, IP addresses, ports, host names, where they are deployed, where they live, all of these should be zero configuration. I think it's apparent from the name. Zero configuration means without any human involvement, without any manual configuration. Now, what we did before, like 10 years ago, would be to manually configure IP addresses on our load balancers, on our reverse proxies, where that service would reside. You would manually update, or over a system, you would update a list of IP addresses for the service. And then recently, people started to use technologies like Zookeeper to keep track of these changes, where each service is deployed and what it's responsible for and how you need to route to it. Now, your microservices application, whether it uses Zookeeper or not, should be zero configuration, not only in auto-discovering new services, but also in scaling up services. So you should be able to individually scale up the purchase service without breaking anything. And it should be automatically visible to the API gateway. It should be automatically visible to the other services. And multiple copies of the same purchase service should be able to talk to the payment service or the user service or the log service or the database. And here's the important bit. It's not as easy as just scaling the number of containers you have in your Kubernetes environment or in your Docker Swarm environment. What you need to do here is you need to make sure the application architecture is safe to be replicated. For example, if you're keeping any state in memory, this won't work. If you're keeping any shared state with the ID of that service, it won't work. It has to be infinitely replicable. You should be able to replicate any service, and it should happen automatically, autonomously even, without any configuration. And this is the second rule of microservices. Obviously, what follows from the second rule, once you establish zero configuration, you can make your application highly redundant, which means your application can run in any cloud without any restriction, and it can run in multiple places. You can have multiple copies of the same service, even if they're idle, even if they don't serve any traffic, they can be lying around. Or in case of demand, which is something we're going to talk about next, you should be able to spawn new services. So highly redundant systems are those systems which tolerate failures. Again, we're going to be talking a little bit more about that in a second. But the capability of your application to go highly redundant is really important. And now, in my experience, the biggest problem with highly redundant systems is when it comes to publish and subscribe patterns. It's very easy to scale systems that are serving some requests and some responses. It's easy to scale services that don't have any side effects and that don't have any local state. That's great. But when it comes to publishers and subscribers, but if you scale your publishers and those publishers, they receive the same message and then publish it twice to your internal system, that is a huge problem with making your system redundant. So then you have to form certain practices where, through a gossip protocol, they come together and they elect a leader, and the leader publishes the messages, and the others are just voting who the leader is. And once the leader goes down, the others elect a new leader. The other publishers in the system elect a new leader. There are many alternatives to making your system highly redundant. But what this rule is about is ensuring that your application, every piece of it, can be scaled automatically, autonomously even, again, and that we eliminate single points of failure. But obviously, even if we scale everything up to all the availability zones, to all the data centers we have, there still might be certain problems, and faults will appear all the time. And what we have here is rule number 4, fault tolerance. Your application should not break when one of the services go down. Now, this is extremely, extremely important. And this is a huge distinction from the actual monolith architecture that we have. Now, the reason for why I defined what is not a microservice in the first place is because a lot of people think when they break down their monolith, it's going to be microservices. No, that's what we call a distributed monolith. And this is a clear differentiator. When one of your services go down, in this case, the payment service, if all the application goes down and it cannot serve any requests whatsoever, then that means you're not doing microservices. And that also means your application is not fault tolerant. What should happen in this case is if the payment service is down, people should be able to visit the homepage and go through the catalog. They should be able to see what you have in store. And even the purchase service is up and running. It just can't do payments. So it can do, I don't know, all the other functions it should do, like credit card validation, inventory checks and everything, or address checks and everything. But it just cannot do payments. And that is how you should contain the fault. Obviously, what happens if purchase service is up and payment service is down? It's going to be receiving requests. It's going to be talking to the user service to validate the identity of the user, which is great. But when it comes to payments, it's going to time out, or payment service will be down. It's going to receive an error. What happens is those requests will build up in the purchase service, and it won't be able to fulfill those requests, which means it won't be able to fulfill the requirements or the request of the users. And if you don't handle faults very well, and these requests that go to the payment service just time out, what happens there is purchase service becomes a bottleneck. You have to scale it to infinity because apparently it cannot handle the load, because it's just waiting for the payment service to give it an answer. Now, this is why I'm talking about fault tolerance. There are several different techniques that you can build in order to combat faults. And one of the useful patterns is a circuit breaker. If the payment service is down, you should know that the circuit is not closed, which means it's open, which means there's no electricity flowing. I know it's a little bit unconventional, but the circuit is not closed, and therefore you have to break it earlier. So all the requests that will end up in the payment service, you should identify those requests. All the requests that will end up in the payment service should be blocked at the gateway. Now, there are, again, multiple ways of achieving this. It is extremely difficult to implement a true circuit breaker. What usually happens is people just cut out purchase service entirely. And there you lose some of the abilities of your application to run self-contained. For example, the purchase service should be able to return the details of the previous purchases, of all purchases, right? It has nothing to do with payments. It's just a record in its database. It's just going to return those records. If you completely eliminate purchase service out of the equation, you don't get any of these things. This functionality will be unavailable to the users. And that also shows us that you need to work on your microservice application a little bit more. Now, obviously, what follows from fault tolerance is self-healing. Your microservices application should be able to heal itself automatically without your intervention, without even alerting any of your monitoring staff. So nobody should be paid just because the service is down. What should happen is, yeah, you might lose a couple of requests. Hopefully you don't, because that is also another technique for fault tolerance. You just keep on to those requests if you know that your system will be healing itself. If you can spawn new payment services in a split second, which some systems can do right now, you can say, okay, I'm going to hold on to the request that has failed in the purchase service, and I'm not raising a flag, I'm not alerting anybody else, and I'm not doing the circuit breaking pattern. I'm just going to hold on to those requests because I know the payment service will be back online in a couple of seconds, and I'm going to retry those requests. And obviously, what happens if you sent that request before the payment service already processed it, and then you're retrying it? That shouldn't end up in charging the customer twice. Your payments and your requests should be idempotent, and this, entails a huge discussion on how to implement those systems very well. But what we focus on, rule 5 here, is self-healing. your system should be automatically spawning new services that have failed. If the payment service is down and it's not restarting, what you should do is you should automatically, again, create new copies of the payment service, maybe in another data center, maybe in another availability zone, I don't know. But coupled with the first rules of zero configuration and auto discovery, what we have here is the new services will be picked up by the purchase service. The requests will be routed to the new payment services. And the retry mechanism doesn't have to be dumb in this case. If you have auto discovery, what can happen is payment service says, hey, folks, I'm online. Sorry, there was a glitch. I was offline. Now I'm online again. So you can now continue sending me your messages. And then the purchase service knows when to dump those messages into the payment service instead of, in a stupid fashion, just repeating the requests over and over again until the payment service is online. That doesn't work. That is not an intelligent system. Please don't design systems that way. Okay. Now, we were talking about Rule 5, self-healing. And if you didn't notice, we're basically over all the 5 rules of what makes a great microservices architecture. Now, how do we have these? This is a huge question. There are, as a groundwork, there are some technologies that we use today to enable the 5 rules of microservices. Most of the people use Kubernetes. There's also the alternative Docker Swarm or Docker Enterprise that you can use that orchestrates your environment. Now, obviously, you don't have to do microservices on Kubernetes or Docker Swarm. You can just have your regular applications. But what happens is when you have a microservices architecture, Kubernetes and Docker Swarm have some tools built in them that help you out. And they're called orchestration services. They orchestrate the deployment, security, network management, fault tolerance, and several other aspects of your application. So let's see what they enable. They enable, sometimes out of the box, sometimes you have to configure them, and sometimes you have to even build software to enable some of these. But out of the box, they enable at least the groundwork for auto discovery. They give you rollouts and rollbacks. They give you self-healing. And I think this is what they're best at. When a service goes down, you have certain health checks, and it's very easy to put those services back online, to spawn them maybe in a new location, in a new service. At least the orchestration services like Docker, Swarm, or Kubernetes take care of these. And one more important thing is they also do secrets and configuration management for you. So obviously, most of the operations should be zero configuration, but your application might depend on certain configurations, like certain keys for the third-party systems that you use. And you should be also automating the delivery of these configuration. And orchestration services help with that as well. Now, what these cover, not entirely, but at least the groundwork for, are 4 rules: auto discovery, zero configuration, highly redundant systems, high redundancy, and self-healing. These 4 rules are pretty much covered by the orchestration services that we have today. And again, remember all the things I said about these rules. Maybe there are Kubernetes practitioners among you right now. Think about all the daily chores that you're doing on that system, on the application, and compare and contrast whether they fully cover these rules. But there is one rule that we didn't cover at all, and that's fault tolerance. Now, I talked about circuit breakers as a viable pattern so that you cancel the requests at the gateway level. You cancel the requests that you know will go to the affected service, the service that's malfunctioning, and you shut them off at the gateway level. That is what a circuit breaker is. How do we do this? There's no out-of-the-box solution in Kubernetes or Docker Swarm for circuit breakers. There are retries. This is also sometimes in your application logic. You might want to have certain retry functionalities or implementation for certain pieces of your, certain critical pieces of your software, and maybe some others don't really need to be retried. How are you going to do these? And the other one is timeouts. Now imagine a long chain of services, like 10 services. Well, the first 4 is great. The 5th one takes like 30 seconds, but it's working. It's just working slowly. Your request timeout is, let's say, 35 seconds. It passes, but there are 5 more services in the queue that you're waiting. And the next one takes about 10 seconds and you're dead. In the gateway, you turned off the timeout. The timeout is over. The wait is over. We're canceling that request. How are you going to keep track of this and make sure you unroll every change you did in this perfectly fine system that is working as intended? It's just a little bit slow. How are we going to make sure that we propagate that timeout to the rest of our services? Now, this happens when you rely on a third-party service. It's just very slow. And, sometimes it just doesn't respond in time. It's totally out of your control, so you cannot really control or, scale it up. So how are you going to deal with timeouts within your system, within external systems that affect you? And how are you going to retry the request, which you don't know if it failed or not? These are open questions that I'm asking to provoke some thought, or as other people say, food for thought. Now, there is a technology called Istio that enables most of these scenarios very, very well. What Istio does is you deploy it alongside your Kubernetes application. For every pod you have, it deploys what is called a sidecar, and it basically takes over your communication and everything. And it gives you all these patterns, circuit breaking, retries, timeouts, and everything almost out of the box. Obviously, this means a lot of configuration upfront for Istio to run. But once you have it, then your application can run pretty much with all of these patterns built in. And that is how you enable Rule 4. All right. There are a couple of other concerns of modern applications that we have left out that you have to deal with. Obviously, this is a talk to cover the 5 absolute must-have rules of microservices, and then there are other stuff that you should be thinking about. And the first one is observability. The second one is tracing. How do you know which requests go where, which requests hit what service, where is the bottleneck, and can you trace a path for a request? The purchase request goes from this service to this one to that one and ends and hits database and then comes back and then goes to another service. You should be able to trace this in order to debug your application, because debugging distributed applications is maybe one of the hardest things in modern software engineering. Then you have authentication and authorization. Are these services authorized to talk to each other? How about what if some third party is impersonating the purchase service that I have? How do I make sure that they're not an imposter, but they are the actual service that I want in my system? So you have to introduce certificates. Hopefully you have public key cryptography in between these services. And then you have to introduce, especially when you're scaling beyond a certain number of services, you have to introduce roles and permissions so that anybody can develop any service, but unless they get certain roles, they cannot do everything in the system. And then you have to, propagate the secrets. You have to cycle and roll your certificates. You have volumes that you're attaching to certain services, and what happens when those systems go down, and when you want to replicate them, do you replicate the volumes as well, or do they share the same volume? What happens if they're on different data centers? These are all the questions, all the problems of modern applications that we have left out. And I know it's a little bit overwhelming, but I just wanted to paint a picture of what good microservice architectures are and have in common. And well, it's a lot. It's a lot to absorb. Now, before I finish, I want you to remember this. All microservices are distributed applications, and that's for sure. The thing is, not every distributed application is a microservices application. So microservices have to be distributed over the network. They have to communicate over the network. But not all applications that communicate over the network are microservices applications. And today, I hope I could give you a little bit of info and insight into what makes an application a proper, good microservices application. Thank you. All right, now I think I don't know if we have time. Okay.
On Crowdcast, and I sent you the first one through our chat because it's a bit long, so it's probably better if you read it as well. Related to rule 1 auto discovery, what if I have a new service added, like checking a customer credit score that will be called from purchase service? The service by nature will be auto discover, but I still have to write code in purchase service to make use of the credit score return results and redeploy it. What is the correct approach?
So this is a very common scenario. The dependencies are not gone. So even if we build microservices, the dependencies will always be there. It's impossible to break these dependencies. And unfortunately, this feels like you have to have some sort of concerted effort for deployment, because we have to deploy to make use of that service. So the best way to approach this is to heavily invest in feature toggling. So what you do is that service, that credit score service goes online, but regardless of whenever it goes online, in your purchase service, you have a feature toggle that knows how to communicate with a future service. This is what I mean by auto discovery. You will write the code first by using whatever means you use. Is it an event name? Is it a host name, a made-up host name for the purchase service? But when you deploy, for the customer score, credit score service, but when you deploy the credit score service, it's going to say, hey, I'm online. And hopefully you won't be bothered to toggle that feature toggle yourself. The system will just start talking to that. Or, you will manually turn that toggle on so that the purchase service can start talking to the credit score service. So basically, this is one of the best practices of refactoring, and it applies here 100%. I hope that was enough to answer the question.
Well,
if there are any follow-ups,
there's a second question. Regarding configuration management and inventory management in microservices architectures for addressing static, dynamic, functional, technical aspects, what would you recommend? Manage CMS, CMDB, feature flipping, service mesh, K8s, config maps, GitOps, other patterns or solutions combinations? Again, a very long question.
Yes, this is a great question. And I think we could have an entire conference just based on this, answering this question. But yeah, we already talked about feature toggling. I think feature flipping is what it refers to. A service mesh is what I'm referring to with Istio. Istio enables a service mesh. And essentially all microservices applications are a mesh network application, in that arbitrary services can talk to other arbitrary services, and you don't really care who's talking to what. And in that, using Istio Kubernetes really helps. Obviously, we try to move as many configuration as possible to config maps to environment variables and not really ship any configuration within the code, because we never know when certain things will change. And this actually applies really well with Liskov substitution principle that Alex talked about. In that, certain applications might change behavior by configuring them, without ever touching the code. It's just a microservice that you take from somewhere, you configure it, I don't know, give it some endpoints, some pre-configuration over environment variables, you deploy it, it works, nobody knows what goes inside, and that is the entire point of microservices. We shouldn't care what goes inside there. And yeah, GitOps, again, these are all the best practices. Thank you for the question, Valentin. I think these are all the best practices that you should be implementing in your microservices architecture. And unfortunately, again, the biggest hurdle, the biggest issue here is communication and therefore cultural challenges of microservices. I don't really see it as a technical problem because there are multiple solutions to all of these problems, but we couldn't really solve the one big issue of this distributed application. How do we manage distributed teams that act on their own, and how do we make sure the system operates without a fault? Thank you for the question.
Okay. There's a third question. People have been adding some. So what are the best persistence databases to use with a microservice? I guess that depends on the use case, actually. Exactly.
That depends on the use case. And you can use any database. Nowadays, and mostly I prefer NoSQL databases like MongoDB, especially after it started supporting transactions. It's a little bit better. But the idea is your requests have to be idempotent anyway. So anything you write to the database, you should be able to write 10 times. The same query, you should be able to execute it 10 times. And it shouldn't break anything. You shouldn't be inserting 10 new records. That's why I think, and especially when you have to decouple the systems, I think document databases are a little bit suitable for these scenarios. But obviously, there are certain scenarios like payments and other transactional areas where you cannot really rely on something like MongoDB, that you have to keep relational data. Maybe you're going to use a graph database. The idea is anything that allows you to build isolated data in an idempotent way works, basically.
Perfect. And the last question that we have here, what is your opinion on feature toggle, maybe used excessively or introduce a huge technical debt? I guess it says depth, but I might
miss that. It's feature toggles are a huge technical debt. All my applications are junkyard of feature toggles that we never clean. Now, let's face it, all of us do it. We have a lot of feature toggles. We have a lot of branch by abstraction, and all the abstraction methods, we just don't clean them when we go to production because we're running to the next feature. And yes, this is a huge issue. That's why kind of microservices being small in their code base help, because at least how many toggles can you have in 200 lines? 10 of them. At a certain point, it becomes really bothering, and then you start cleaning them up. Still, I use them excessively for ensuring the health and the stability of my systems. However, it's still a graveyard of feature toggles. There's no way around it.
Okay, Armayan, thank you very much for this talk. It was very insightful.
Thank you.
As I expected from your own experiences with working with the microservices. That's great to hear such practical advice.
Thank you.